So for my final project today, I'm going to present a brief overview of supernovae. I'm going to start with a brief review of some of the material that we've already covered in class about supernovae and the death of stars. And then I will get into a bit more of the history of how scientists have discovered and observed supernovae before I get into a bit more detail about the different types of supernovae and their relevance to our understanding of the universe. On your screen here, you can see an image of the Crab Nebula, which was created in the aftermath of supernova 1054 in the year 1054. So first, a quick review. What is a supernova? As I said, hopefully you recall most of this from class, so in the interest of time, I'm just going to highlight a few key ideas. Supernovae generally occur at the end of a massive star's life. Thermal runaway or runaway fusion is the other instance in which a supernova can occur, and we'll get into this a bit more when we look at the difference between type 1 and type 2 supernovae. Core collapse, however, is the most common form of the supernova, and it occurs when the core of a star runs out of fuel, essentially, and the electron degeneracy pressure can no longer support the core against its own gravity. At this point, the star collapses, and there's a very bright burst of light and a massive and rapid high energy shockwave. For some perspective, the energy emitted from a typical supernova might be greater than the total amount of energy that our sun will emit in its entire lifetime. A star then may either turn into a neutron star or a black hole as a result of this explosion, or the star may just be completely destroyed. So next I'm going to walk through a brief timeline of observed supernova and their importance in our understanding of this phenomenon. In 185 AD, there was the first known observation of a supernova, known as RCW 86, which was observed by Chinese astronomers. There are potentially earlier observations from a few thousand years prior, but this is the first confirmed recorded observation. Moving along to the year 1006, astronomers across the world observed what is considered to be the brightest observed supernova, named supernova 1006. As you can tell, the naming of these supernovae is very creative. This supernova was so bright that people reported being able to see supernova 1006 during the daytime. Just about 50 years later, in 1054, supernova 1054 was also widely observed and ultimately created the Crab Nebula that was pictured on the title slide. In 1604, Johannes Kepler was among those to observe supernova 1604, which is the most recent supernova to have been observed directly with the naked eye from Earth. This supernova was also important in refuting the belief that the universe beyond our solar system was unchanging. It wasn't until the 1930s, however, when this term supernova came into being, as it was coined by two astronomers named Walter Baade and Fritz Zwicky. The modern advancements in telescopes have made distant supernovae somewhat more commonly observable. And one interesting story that I came across while doing research was about an amateur astronomer in 2016 who accidentally came across a supernova that was just becoming visible on Earth while he was using his telescope to take pictures of another galaxy. This was the first time anyone had captured the earliest visible moments like this, and one astronomer estimated that the chances of viewing such an event were between 1 in 10 million and 1 in 100 million. Here's an image of supernova 1006. It's a composite image, so you can see the X-ray data is in blue, optical data is in yellow, and radio image data is in red. So as I said, there are two main types of supernovae. With type 1 supernovae, absorption lines in the spectra show no hydrogen. Thermal runaway is particular to one subgroup, the type 1a subgroup. In this case, a star, typically a dwarf star, collects matter from a nearby neighbor, in which case the core heats up and compresses, leading to this runaway fusion, which results in a supernova explosion. With type 2 supernovae, absorption lines in the spectra do have hydrogen, and all subgroups have the feature of core collapse. With core collapse, the core uses up hydrogen and helium, and then the fusion of heavier elements as the core heats up further. Eventually, this fusion can't sustain the core against its own gravity, and when the core reaches a certain mass, at the Chandrasekhar limit, the star collapses. So in conclusion, why are supernovae important? Beyond the cool pictures, of course. Supernovae are a source for a number of elements in our periodic table, including some pretty important ones such as iron, neon, oxygen, and more. Secondly, observation of supernovae have acted as proof for the expansion of the universe, as I talked about earlier with Johannes Kepler. And finally, remnants from supernovae produce new stars, planets, and everything else that is found in our universe. So thank you for listening to my presentation, and here are the sources that I've used.